Now, Newton's law, of course, explained very nicely the average property of orbits of planets around Sun. But there was one tiny little problem that kept plaguing the astronomer's curious mind, and that was the anomalous precision of Mercury's perihelion. Perihelion is the point of the closest distance of Mercury from the Sun. What astronomers, through their meticulous observation, what they found was this point was not fixed. As years go by, the point keeps on shifting. Now, of course, to a large extent, the shift in the perihelion comes about because of the perturbation of the other planets. But even after you have included that, you find that the shift in the perihelion of Mercury is about 43 arcseconds per century. And this number was termed as anomalous because Newton's gravity could not explain it even after including the planetary perturbation. It was Einstein who, using his relativity and giving a geometrical interpretation to gravity, immediately explained why perihelion of Mercury precesses. Now, Einstein's view of gravity was very different from Newton's gravity. Although Einstein's theory in approximation gives rise to Newton's theory, Einstein said gravity is not a force at all. Instead, gravity is nothing but the curvature in space-time brought about by massive objects. So whether it is Earth or whether it is stable chair, anything that has mass and energy would distort the geometry of the space-time around it. So it was the geometry, because near Sun being a very heavy object, if you are very close to Sun, the geometry is very distorted. And since Mercury is the closest to Sun, it sees the geometrical effect more clearly, and Einstein explained that it is due to the curved geometry that Mercury's perihelion precesses. Now, from his theory, what it turns out is that actually the parabolic trajectory of a particle, which Newton predicted in a gravitational field, that trajectory is not a curved trajectory. Rather, in Einstein's theory, because the geometry is distorted, the trajectory of a particle is nothing but the shortest distance. For example, on a curved geometry like the surface of the sphere, the shortest distance, the straightest path are the great circle around the sphere, and the great circle, they always converge. So as though there's an attraction. Now, because of the change in the geometry brought about by massive objects, Einstein predicted that if you have a massive object like a star or a galaxy, and if you have a star in the background, then the light from the star, it sees a distorted geometry, and therefore apparently the light rays, they get bent and they reach the telescope of an observer here. But because the light is bent, the observer sees an image when he extends this trajectory, and there's also another image. So Einstein predicted that the distorted geometry around a massive object acts like a lens which splits the light rays, and this gravitational lensing was observed by astronomers. There are numerous cases of gravitational lensing. For example, here typically we show that Earth lying in the Milky Way galaxy here, and if you are looking at a distant galaxy through the telescope, but in the foreground of the galaxy there is a large clusters of galaxies where there are something like 1,000 galaxies within a few thousand light years bound to each other. So it's a very massive object, and the light rays from the distant galaxy, they get bent because of the distorted geometry around the cluster, and this bent thing would give rise to multiple images of the galaxy, and astronomers very frequently see multiple images of an identical galaxy or a quasar, and these are called gravitationally lensed objects. And this comes about because of distorted geometry of the space-time. whole idea of the Big Bang, that is, universe is expanding all through. This expansion of the universe also comes about because of Einstein's theory of gravity, which today we call it general theory of relativity, which essentially says that the space-time geometry is changing with time, so that the distance between any 2 points is increasing. And it is this increase in the distance which causes the wavelength of light to be stretched, and this redshift of the light we observe today, so that further a galaxy is, as the light ray comes to us, it takes a huge time. Within that time, the light ray, the wavelength of the light gets stretched, and we observe the spectrum to be redshifted from a distant galaxy. And this results in the Hubble Law, which says further away a galaxy is, faster it moves. Today we don't say faster, but further away the galaxy is, more time light takes to reach us, and therefore the wavelength of the light is also stretched longer. All this is due to the geometric theory of gravity which Einstein proposed.